Okay, how are we doing? Are we live? Are we here? Howdy. Hello! Is it working? Is this thing on? Is this thing on? I think so. Alright. So, hello and welcome. Howdy doody. Guten Abend. Good evening. I wanted to put together something. I was watching some things. So I watched a lot of stuff today, I guess, and I wanted to talk about some of those things. There's so much to talk about. There's so much stuff for me to do too. It's too much. Just want to take it easy. Just go slow. Just just not worry about all these things. Like all these things to worry about. I don't want to worry about it. Just don't worry about it. One of those things. Just not saying so much. There are these stories about. I don't want to go into it just yet, but basically these stories that I heard, I've been thinking about, of like a guy had a younger sister. The younger sister was molested. The guy tried to kill the guy that tried to molest his sister. The guy went to prison for trying to murder somebody, and it ruined his life, right? And he basically has been in jail his whole life, 15 years, something like that. He's only 33. And he kind of doesn't know how to come back into society, something like that. And there's a few things to say about it. Apparently he was a Christian before doing this. And he nearly killed the guy. Like, he basically stabbed him a bunch of times and busted up his face in kind of a pretty brutal way. And he was, he's professed to be a Christian before doing these things. And it makes me think a lot about, recently I've been thinking about this idea of revenge and grace, and basically even if someone genuinely did something evil to you, to not seek revenge for yourself, for your own sake, but to seek justice as is right, and also to seek whatever you do to seek God in the process. Like, in other words, to honor God in all that you do. Even when someone did something very evil to you, right? Because, I think about that. Like, you have the right to defend yourself, but you don't have the right to kill somebody, right? Even if they do something evil to you. Now, if you happen to kill them while defending yourself, that's a different story. But obviously, you're even compelled to not kill them if you can, right? Because it's a sin, right? Thou shalt not kill. So, and I've been thinking a lot about that. I've been thinking about these different ideas about revenge and how to treat other people and what to do, and there are these different stories of, like, there's something you think that might be really minor, minuscule, like telling your 1-year-old daughter that if someone were to touch her, that you would kill them, right? Someone ever touched her, that you'd kill them. And that to you might not seem like a big deal. I mean, obviously it's inappropriate when you think about it. With a clear head, you realize that a 1-year-old doesn't even know what that means. Obviously, if you want your kid to not get molested, you would have to tell, one, don't let your kid out of your sight, for starters, if you can, and don't do it in a way that's cruel or evil, but do it in a way that's, what do they call that? Reasonable, within reason, as much as you can. Yeah, basically don't let your kid out of your sight, and within reason. And also gently tell your kid, if someone touches you, I want you to tell me immediately, right? And you don't have to explain to your kid why, you just tell them that. Say, if anyone touches you, let me know. And you could deal with it after, you could figure it out. Obviously you want to prevent that kind of thing. And you might not think it's such a big deal to express that anger to your child. Even, it's obviously it's wrong, because it's pretty clear that it's wrong, at least in the sense of, like, what's that going to accomplish? Because your kid just might get molested and then be afraid that you're going to kill somebody and not tell you. And then that kid is going to have to be in a tough spot, which is something, you don't really think about stuff like that. as a man or just as a person. You don't realize sometimes the expressions of your anger, the threats against God that you make just carelessly to anybody that you might be dealing with, even if in your mind you think, well, what harm could it do? What harm could it possibly do? God's grace is amazing. However, there is sort of a, I guess, don't take it for granted. Is what I want to say. Don't, grace is important, and showing grace to other people is important. And being gracious is important, and it's hard to fully express how these things play out. And so I did want to talk about some things, and it takes me some time to kind of put it together, and I feel guilty about not doing other things because of these other things on my mind that I keep saying, oh, I got to do these other things too, and I'm slowly losing my sanity because it's too much. And all I want to do is just sit here and just have a really simple, just get off of work, go do programming problems, but actually I'm probably already at a point where I don't know how many more of these problems I really need to do. I mean, there's almost no point other than for therapeutic reasons, just to get my mind to, just focus on something else for some time. Actually, because if I want to get a job, I mean, I already have a pretty good job. I really don't need another job. I think I mentioned I trade options, and I'm looking to make today I could have made I would have made $5,000 today if I held my position. And that's the past few days have been like that. Make $5,000. Actually, it would have been 5 times. I would have made 5,000, 25. I would have made $70,000 in a week. I don't know, man. I'm kind of a lucky guy. I don't know. I shouldn't say that. Thank God, right? Thank God. I'm not trying to be that bold, though. I don't want to take that kind of risk. I want to be a little slower about things. But yeah, I've been feeling that level of confidence lately where I could actually do even more than that. I could make $700,000 in a week, potentially. Although, again, that probably won't happen, right? If I take that amount of risk, I'll probably just fall on my face. But anyway, yeah, it's I don't really need to do. I don't know. I don't know. I don't know. I don't even know anymore. See where I'm at in 6 months, and I want to. I just want to do something simple. Just solve a computer science, solve a programming question. Just do that. Just relax. Do that. You can figure out your other problems on the way, right? Whenever. Don't need to do it now. And you could talk about what you're learning about really keeping my mouth shut. I mean, if I was more of a person who just wouldn't speak very much at all about anything, I would avoid situations like that where you tell your daughter something unnerving that actually causes serious problems for her later. I would avoid things like that if I just keep my mouth shut. The machismo, it's not needed. You don't need that. No, I don't need that. Relax. Relax. Anyway, okay. Let's dig into these problems. Let's take a look. Let's take a look and get acquainted with something that's a little more. I don't know. I don't feel guilty. I just feel guilty. That's the thing. Somehow, some way. I just have this very uncomfortable feeling I should be doing more somehow or something. Somehow I'm not doing enough or something. I don't know. It's weird. It's a weird thing. It's a weird feeling. I want to. Yeah. All right. So we'll get into this problem. So let's do that. Just take a moment to kind of express my thoughts, I suppose. And what do I want to do? So let's go here, normal, and say howdy. All right, maximum size subarray sum equals k. All right, let's go for that one. Let's go for it. Let's go for it. Given an array nums and a target value k, find the maximum length of a subarray that sums to k. If there isn't one, return 0 instead. Given an array nums and a target value k, find the maximum length of a subarray that sums to k. If there isn't one, return 0. The sum of the entire nums array is guaranteed to fit within the 32-bit signed integer range. Nice. That helps. Is the longest. Okay. Subarray -1, 2 sums to 1 and is the longest. Huh. Interesting. Can you do it in linear time? I believe you can. So this is like a variation on a subarray sum problem, which the subarray sum problem would be find the. I want to say it's the really it's find the largest sum of any consecutive subsequence. That's the largest subarray sum problem. That's like a classic problem. This one seems related. This may not be the same. Like it could be quite different. But let's see how we do. Yeah, this could be very different. So let's say like a brute force approach, or let's just say like the approach, the largest subarray sum problem. What you would do is you would find at each index what the largest subarray sum is from that index, and then the largest subarray sum for the whole algorithm must be the largest of those. So at each point there's a sum that contains that. It starts at that index. Starts at that index. And so you could calculate the largest subarray sum, and actually the way you figure it out is you for the sum that you're calculating from that point, you would keep adding positive values, and then when you see a negative value, you actually stop there. Or what do you do? No. Do you stop there? You don't necessarily stop there, because actually what follows the negative values could actually be worth adding the negative values. So you would want to keep going from there. So there's another way of doing it, but you can do it that way, where you just kind of left to right find the largest sum, and your largest sum would, like, once you find a negative value, you kind of have to save that largest sum there, save that point, and until you find something that exceeds, as you go to the right, until you find something that exceeds that point, you would replace it. And what happens is, so this would be O of n squared time if you do it this way, where you go at each index, go all the way left to right, and go through the loop through the whole thing each time, and then do one more loop at the end to find the maximum of all of those. However, what you actually can do is update the maximum. You can actually do them all in sort of one step. And so what happens is you have once you see a negative number, you have a maximum already that you can consider. And actually, you don't even need to check if it's negative. You can just check. What you would do is you would take the maximum sum would be the maximum of the current maximum that you have, and x, we'll call it, and either add that value, meaning that you're not going to change, you're not going to update your starting point, or you're going to have a new starting point at that spot. So either add the value or you start fresh there. And so you take the maximum of those two values, and that gives you like your running sum, and what you return is going to be this return value that you keep track of. You're going to actually update it to the larger of those two values at each step. You do it that way. That gives you the maximum subarray sum. And the reason for that is each sort of left to right, at each point where you begin your subarray sum, you're basically deciding, do we want to start here or not? And because you're sort of moving left to right, it's pretty much always better to not start a new one if you've already got some sort of positive value already. You've already got a sum that's good to have, I suppose. And then you're going to add this next element. That's going to be better. You wouldn't find a better sum. You can basically skip calculating that particular index. And not only that, but if you do hit a point where it would be better to start fresh at that index, meaning you've added a bunch of negative values, really is what it comes down to. You've added a bunch of negative values, so much so that it's actually not even it's not worth going all the way through the negative values. Then that's basically what you've discovered. It's not worth it. So let me start at this new index, which is what you would have discovered anyway if you had sort of if you had actually calculated, so you could skip that too. And so as it turns out, and then once you've stopped, and by the way, at each point you have that sort of running sum. You keep checking that against the total maximum, because it may be the case that before you actually, you want to encapsulate each index, right? That calculation at each index, that maximum subsequence sum at each index, you want to encapsulate that. So that's why you have the running total also. So you have two kind of maximum values that you're checking, and it's actually extremely short piece of code, and it's very interesting. So this one is probably similar. This is the longest subarray that sums to k. So we may be able to do a similar algorithm, although now we're taking the longest subarray, which we do want to keep a sum. And basically, we could do the same quadratic algorithm. Like, let's code that. That actually would work, because that at each index you could say find this property, right? And then loop over that at the end. So let's do that. Let's try that. So let's say vector int 4 is the number. So we want to say best at index, or best per index, or longest per index, we'll say. Right? And we want to actually make that nums.size sort of at 0, that we would say we can't even get to k. Now we say for each index I, so we could do this too. Let's just find something that seems to be correct. Let's start with that. For each I, you're going to say for int j equals I, j is less than n, right? Left to right. Let's say we have a sum int total equals 0. Total plus equals nums of j. And we say if total equals k, then we're going to take longest per index equal to the maximum of itself of I, and we have not just a total, but we have also the length. Starts off at 0. length plus equals 1. Just do plus plus. And the length. And otherwise, so now the question is, yeah, I mean, yes. So for this algorithm, we could have a similar situation where we hit k, then we go over k, then we go back under k, and then we come back to k, and we can actually have this maximum hit a few times. So we would want to go all the way through, and then at the end we're going to do another routine, which we're going to say for int I, or we can even do it this way, auto x in longest per index, and say we can actually do max element. It's probably better. Return max element. Right, something like this. And do one more linear search. So this would be, I believe this would be a correct algorithm, but it would be inefficient. If I can remember to, yeah, if it compiles, if I remember to write this correctly. What do you say, 2? Okay, so I think this is correct. Now, what we want to do is we want to optimize this somehow, right? We want to do it in linear time. Because right now this is quadratic time. Now, because we're going through the loop twice, each, you know, one outer loop and one inner loop. Now, what I suspect is that we can actually replace this. Well, what we want to do is have a maximum length. I wanna not use this longest per index, and I want to have this maximum length here. So have this length of 0, and as you go, you update this length to, or we'll just say we'll have a current length, right? Current length, and we'll have a longest or max length, right? And we'll say plus length and say max length equals the maximum of current length of what max length is at the moment and what current length is. So we've got this max length, and then we say, we do it this way. So if total equals k, then update this maximum length, and then we'll update this to max length as well. All right, hopefully that makes some sense. So let's see if that still works. Yeah, that's expected. So we're gonna have this maximum length that we update as we go, and don't necessarily need this longest per index here, because you can actually take our return value and say at the end of this, ret equals standard max of ret and max length after this routine, and you can return ret. I believe, right? I believe you can do that. Yeah, still get the same answer. So you don't need this longest per index anymore. So we've effectively removed that. Great. So we don't have that array anymore. Now the question is, do we still need 2 loops? Right? Can we do something similar to what we did for the other question that I was just describing? Can we actually combine these 2 loops? And we might be able to. So we have our total, which now that's a good question. That's a good question. Can we do that? Can we update our total to something else entirely? So let's say we're no longer equal to k. Let's say, right, so we've got this sequence looping from left to right, and we want to decide whether or not we should start at a new index or not. I actually think we won't be able to do it this way, the way that I'm describing. I think better off, we're actually better off using a sliding window. Possibly. No, maybe not. Just thinking, this works. This is a brute force approach, but we want to do it more efficiently. Let's think about how can we do that more efficiently. Don't have any ideas offhand. Let's just think if this is possible, if we can, that we know it includes a particular index, a subsequence that we know includes a particular index. Excuse me. Well, subarray sums, consecutive subarray sums that sum to 0 can always be appended. So that's one idea. However, I think finding all of those and combining those with the ones that sum to k maybe is not the best idea. Maybe there's a way we can do that sort of in tandem. Sort of implicitly. If we add these numbers, so the thing is, like, we can end up subtracting a lot of numbers and then adding a few very large positive numbers and end up at k, where we would want to skip the new indices that we could have used. Maybe we'd want to go backwards from the whole sum. Maybe we start with a total sum of the whole thing, and we would actually subtract values until we get to k. So we would have a subsequence that doesn't include a particular index. Do it backwards. That doesn't seem right. That doesn't seem right. At the moment, I don't see an obvious way to optimize this. But good question. Pretty good question. Definitely has got me thinking here. Definitely has me thinking. So let's ponder it. What could we do? Excuse me. Excuse me. Oh, I have an idea. Oh, wait a minute. Oh, no kidding. Oh, brother. Okay. Actually, we can make things a little bit easier by pre-computing the subarray sums, and so we can actually very efficiently find out what the sum is between between excuse me. I don't know if that helps, but if we use the pre-processing step, we can find out what the subarray sum values are at each step, I guess. And then we can try to find basically differences that give you k, right? Yeah, that would actually be similar to the problem where you have two integers and you want to find these two numbers add up to a certain value or they subtract to a certain value. Subtract to give you a certain value. It really would be y minus x, right? Because it's monotonically increasing. So we'd want to find out if basically there's two numbers there that if you subtract one from the other, you end up with the value that you're looking for. It's actually, you have to be careful with the indices, because it's if you make a cumulative sum from left to right, then you're looking at, if you pre-process it that way, you're looking at sort of b minus a, where a comes before b, or a is smaller than b, or at b, you end up losing those values for a. You end up losing those values. You end up with losing those values for a. You end up with not the inclusive subsequence, but actually somewhat exclusive, which is fine. I mean, you just update the subsequence appropriately. Yeah, so I guess in that case you could use a sliding window. You can kind of go from the left to the right and compare these numbers. It's actually sorted that list. So what would you be looking for? You'd be looking for a difference between these values that's equal to k. Huh. Just thinking like the last two numbers. Yeah, okay, no, I got it, that's fine. Or the numbers themselves could be k, yeah. Right, there's two possibilities. Any of those numbers themselves could be k. Oh, it's not strictly monotonically increasing, that's not true. It could be, and the length of those when you subtract them from each other is also the indices, tells you how large the array is. So like j minus I, these two indices are a and b, b minus a. B would be the whole subarray would be without a, and when you subtract a, which b is the size, a would be, actually, yeah, b minus a I think is exactly correct. It's right because you're not including the ath element. So normally it would be b minus a plus 1 because you're inclusive, but it's actually exclusive on one side. So yeah, it's just b minus a is the length. And you're looking for, so you have length b and sum k, so the value is equal to k, and that's length b to work through. And then you also have the differences. You have to somehow find out all of these spots, all the spots where the difference between these two numbers is k equal to k. which it's not necessarily, by the way, it's not necessarily monotonically increasing because you have negative numbers in there. So I take that back. I don't want to sort because that's not linear anymore. I want to say using this preprocessing step, I think helps somehow. I don't know if it does, but it might. Or not, I don't know. Maybe you don't need it. From left to right. Have this difference between these numbers. Yeah, that reminds me a lot of the subarray sum question, subarray sum problem. This is like the best time to buy a stock kind of a problem, where the difference between values, is sort of optimal. I want to say something like that. I want to say this might be related to that. I don't know if it is or it isn't. I don't know. So yeah, you want the difference between two values to be equal to k. Which I don't know. Gotta think about this one. Excuse me. I want to say the two numbers equal, the sum of two numbers equal a certain value. Oh, actually, you can, yeah, so you can do, it's y minus x equals k, right? That's what you're looking for. And that means that y would be equal to k plus x. So you could put all these numbers into a set and then do a hash set and then search through the hash set for each number, using each number as a key, and say you can put all the numbers in the hash set, and then for each number you're going to, and in the hash set also add, I get a hash map, so it has the index also, the value and the index and its associated index, and then you can loop through these sums and say, right, say you want y equals k plus x, so the number you're looking at is x. It's actually, you want y, so you want k plus x to be present. Yeah, just check, is k plus x there in the set, in the hash map. And if it is, then you can take the difference, yeah, then you can do it that way. That works. You can find it that way. Didn't think to do it that way. There's probably a more efficient way to do it, but I think that would be linear. That would be linear time with linear space as well. Are we allowed to modify the array? I mean, you really don't need to modify the array, so we could do it that way. I don't know if we could do it without any extra space though. I think that's the way I would do it. I like that approach. Let's give that a shot. So we'll do unordered map. It's an interesting question though. Definitely. I mean, I didn't solve it yet, but kind of had me stumped for a short while. Value to index. We want this some sums. And we're going to say for auto, or yeah, we'll do int I equals 0, I is less than n, plus plus I. This is actually going to be sort of an accumulation, I guess, but not, yeah, we'll do it this way. So we'll say total 0, or we'll start off with total equals sum or nums. It's actually, you can even do it this way. You can say sums of 0 equals nums of 0. And we're going to say sums of I plus 1 equals sums of I plus nums of I. Yeah, there you go. Sums of I plus nums of I. So it's the previous I, and I starts off at, it should be 0, and this would do less than n minus 1. And we could do it this way. That works. Also, alternatively, I and I minus 1. I kind of prefer to do it this way. It's just out of preference. Doesn't really matter which way you go. So now we have our preprocessing step, and we're going to say val to index. Also, we can take as we go val to index of sums of 0 equals index 0, and we can say val to index of sums of I equals I, right? And finally, we're going to say int ret 0, and for auto x, well, actually do it this way. 0, I is less than n, plus plus I. Say if sums of I, we're going to do int val sums of I. Sums of I equals k, and we're going to say ret equals standard max of ret and I. Check the sum alone. And we also are going to have, so we have our value, right? And we're going to check the sum alone. Place the value into, check the value against the hash map for a pair. So if we say if val to index of this value or dot count, if that exists, and we're actually going to look for a value plus k, looking for y equals val plus k, such that val minus y equals k, right? Or y minus val equals k. So we say val to index dot count a val of k, say int difference equals val to index of val plus k, minus this I, and then we say ret equals standard max of ret, and this difference. And there's one more issue here where if we take, like, let's say we're all the way at the end, we're at n minus 1 and 0, n minus 1 minus 0. When we subtract the 0, it's actually the subsequence of 1 to n minus 1 inclusive. 1 to n minus 1 inclusive is n minus 1 minus 1 plus 1, which would give you n minus 1, which is exactly n minus 1 minus 0. So we're actually in good shape. We don't need to add or subtract anything here. We can just do this difference. And we don't need to check if these are positive or negative either, because if it's negative, ret starts off at 0, so we don't actually need to bother. And let's see if this compiles. Let's start with that. Wrong answer. Compiles, but the wrong answer. So interesting. So I thought I did it correctly, but I guess I didn't. Let me see. Maybe the idea is wrong. So I set this value to the sums of I. We said we did set up our values to index properly, and said if sums of I equals k. Now in this case, the value to index of val of k, this it basically is equal to k, right? You have this val plus k minus val for some index. You are effectively must be equal to k. And then, right, val plus k minus val would be k. And then so now you update with your maximum value. Now the question is, why and how do we, what do we do? Why did we get this wrong? Maybe is the question I should be asking. So we got 4 the first time. That's kind of interesting. But we got 1 instead of 3. So why did that? Can we? In both cases, there was a subarray. Yeah. So right, this one actually should have reached -1 to 2. Okay, so we should have been this one minus this one. This is sort of 0, 1, 2, index 2 minus 0. We got 1. 2 minus 0. This is -2 is the sum at 0. This is -3, sum at 1. And this is -1 at 0, 1, 2. And so -1, so we're searching for val plus k, which is, we add 2, or do we subtract? Should we be subtracting 2? I don't know. So if we add 2 from this guy, which is -3, we get we're looking for -1. Now we said over here, it is -1, right? So immediately we get this one and this one, and we find this val to index of -1, which is 0, 1, 2. Oh, you know what it might be? There might be multiple indices here that are, oh, I see. That's interesting. I didn't think about that. We don't necessarily want the maximum index. Actually, we probably want to push back multiple indices, potentially. That's kind of interesting. I haven't thought about that. Yeah, the values that you're looking for could have different indices associated with them. And you actually want to check all of those indices. You kind of want the largest index at all times here, right? Because this will give you the largest value at all times. So yeah, you actually do want the largest. I think you do want the largest. I'm thinking about that, like, maybe. And we also want to do if val to index count. Let's do let's just do this. Let's okay. Excuse me. If valid index count of x, then we want to update this to the maximum of and I right, otherwise we just set it directly to I. Yeah, something like this. I want to say I think we don't actually need this. I think this automatically initializes to 0. I think we're okay doing this. I don't think we need all that extra overhead. I think it'll work correctly. So we still got 1 though, which is kind of interesting. I wasn't expecting that. I thought I got the right reason why it was wrong. The wrong answer. So if you have multiple indices, why? Okay. So, all right, we'll just debug it. This is like not something you'd want to do in an interview. That would suck. Sums, let's print the sums that we get. Let's also just do this one, the 2. -2, -4, -5, -3. Oh, that's wrong. What? -2 should be -3 for the second one, and this should be -1 for the third one. What happened? Hello? Oh, that's why. Oh, excuse me. Duh. Okay. Gotcha. Well, that actually kind of would explain why. Yeah, I would have had this wrong if I did I plus 1 and I, and then only I here. Should have been I plus 1 here too. That would have been confusing. Oh, but now it's wrong with the first one. Oh, okay. Why is that? Really? What? 10536. 10536. 10536. Yeah, okay. And output 3, expected 4. Oh, is that right? If we do, are any of these equal to 4? Or any of these equal to 3? Yeah. 1, 2, 3, 4 is equal to, oh, this is I plus 1. That's why. Yeah, that's why. It's a little confusing with this. But this part is definitely, yeah, if the index is 0, right? That's one element. So, all right, let's go for it. Let's go for it. Scared to go for it? I don't know. I probably should do a few more test cases. Let's do like some random test cases. It's not really a good habit to just like kind of just go for it, I guess. Zero. Interesting. We don't need the debug code anymore. So let's do one where we don't. Yeah, we just did that, right? If we do an empty string, some empty list, runtime error. It doesn't say if it can be empty or not. So if sanity check nums.empty. Need to have at least one value in there, as you can see. If there is just one value in there, what do we get? And it's equal to k. And one value that's not equal to k. Let's try that. And let's try some random strings of stuff or random numbers. I don't know. Let's try these different things. You can even have a negative value in there too. I don't know. I don't know what I can do to break this. I don't know. -3. Let's see what happens if we do that. Okay. I guess we just go for it. I don't know. I don't know what test I could think of here. It's probably something. Oh no. Got him. Sweet. 98%. Hey. Sweet. I like that. I like that. Constant time, not constant, linear time algorithm. Pretty good. Pretty good. Now the question is, in the discussion, is there a way to do this without using linear extra space? Because you see we used a map and a vector pre-processing step. That's pretty fast. We're faster than most folks on that one in terms of the final runtime. Well, it took an hour to do this. Okay, it's kind of a lot of time. So now we want to see, what does the discussion have to say? O of n, super clean, 9 lines slow Java with hash map. Clean, one pass, really, one pass, no kidding. Using a map, really an easy problem. Subarray, newer methods, 2016. Oh no. Go back. No. I want to see Stefan's approach. One pass with hash map. I have 2 passes. I went with 2 passes. You can, oh, you don't need to put the sums. You could put the, no, wait, let me think. You could do it backwards. You could compute the sums as you go and put them into the hash map and check the hash map simultaneously. How about that? Mine was pretty quick. Wait, what did I get? Okay, 80%. Yeah, it's pretty fast, but actually you can go, I think you can get to 100% if you do a single pass. I think I agree with what these folks were saying. Put if absent max equals I minus the index or get default. Yeah, I think, yeah, hash map. I think this way, right? That's actually, I'm thinking something like that. So you don't need the sums if you go backwards, right? So you can do int total equals nums of 0, and then you might not even need to do the whole. You could even start off at add 0, and you could even do remove the sanity check too, I think. But maybe we're doing too many things at once. So I equals 0, total plus equals nums of I, and then I don't need that anymore. We say val of total is equal to the maximum of itself and I, and now we can go through this at the bottom again, and val is sums of I. We don't really need that, do we? We can do total. We can do total equals 0 again, and then val is going to be really total plus equals nums of I, and then val equals total. Does this still work? I don't know. We still get the right answer. Sums of I equals k. Oh, we say total of I equals k. And what does that look like now? Yeah, still the right answer, I believe. Yeah, we're okay now. So we don't need that first pre-processing step, or rather, we don't actually need to save all these values into a array vector. And then also we can combine this code into one loop by, instead of searching for val plus k, we can search for val k minus val, I want to say. So we have some value that we're going to put in the hash map, and then we're looking for, so we could say val equals 0, by the way. Say val plus equals num. Have this value, and we can do this check here, and then we can also do a check where we put, not check, but we can put this here at the end, and then we can also say if what's in the hash map is, it's not val plus k that we're looking for now, we're actually looking for, we're trying to go backwards. So now we have val is y. So if val equals y, which equals, so if there's sort of y minus x equals k, val is equal to y, that means that val is equal to x plus k. So val is x plus k, that means we're searching for find x equals k minus y. Yeah. Or no, x equals y minus k. A little confusing. So we'll say minus k now, or k, no, I think it's x, it's y minus x equals k, y is then k plus x is then equal to k y minus k, which is val minus k. Yeah, so if we find val minus k, then we want to, now this is going to be I minus val minus k, if that makes sense, because, and we said val instead of total, right? Do val. Want the largest indices that we can get. So do we still want the largest indices? That's a good question. I actually want the smallest now as we go. You actually don't even really want to update it then, I would say. It would do the minimum. You basically don't update it. You want to have the minimum value there, because we're moving to the right. If we find a value, we want the largest, so we actually want to keep the smaller one that we find, the first one that we find. Could also say, like, if it doesn't exist, then set it, something like that. That's another way. One or the other, the minimum, or if it doesn't exist. I think it's probably better to do the if it doesn't exist. Oh, I did it wrong. Should probably do not val, but like x. So yeah, x. Or not x, y. Let's do y. I like that. I like that better. if, yeah, basically that's 0. Oops. Then we want to val of y equal to I, and then leave it there. Right, I don't want to touch it again. That's what is idempotent. So it gets set once and then you leave it. And so now you want the maximum of, now y minus k, this is I. So let's say we go to 5, so we're in position 6 or index 5, and then we say, all right, index 0 is the value, so 5 minus 0, or rather 1 is, yeah, 0 is the value, but we end up subtracting 0 off. It's sort of 1 to 5, so 5 minus 1 plus 1 would give you 5. It is, yeah, it is exactly this one, I think. I think this is correct. Yeah, let's see. How do we do? Okay, now we don't even need this loop, I believe, right? This is still the same, it's like the same running time. It's just, I think, a little bit faster. Yeah, it's a lot faster. Yeah, there we go. We almost have 100%. We still use the hash map. It's close to 100%. Can we remove this maximum, make it faster? Is there any way to make this faster? I want to get 100%. So close. I want 100%. I don't know that we can. How about, yeah, we'll just leave it. That's fine. That's good. Good enough. Good enough. Pretty quick. Yeah, we got 98%, 99% before 20 milliseconds. I'll take it. Not too bad. All right. So thank you for watching. That's that problem. And we'll go ahead and take a break. I think I'll get some, maybe gonna make some food. Just kind of relax for a few minutes, and then we'll get on to the next problem, do the next thing. So yeah, thanks again. Talk to you soon.